Hi, Stuart again. Today I'm going to talk about some general workflow patterns and some common use cases and some areas where workflows can go very wrong indeed. This is a high-level overview. It's not aimed at any particular set of tools, but rather is a design guide to when you might want to use one kind of workflow over another. So workflow semantics are typically graph-based. If they are long-running, they're called Saga workflows. And if they are long-running, it means there are periods where we can't actually do any processing on the data. We're waiting for something. And therefore, we want to dehydrate or store off our intermediate state to somewhere. And then when processing becomes possible again, we want to rehydrate that state and continue. And this is typical in workflows. It's rare to have a workflow that can flow all in one temporal cycle. In other words, from beginning to end without interruption or need for dehydration. Although, as we'll see in our first workflow pattern, that is an option. And even if there are not an obvious finite state machine involved in the workflow, a lot of common workflow patterns, in fact, rely implicitly on an underlying finite state machine, which is if the state of the data is this, the next workflow step to process is that. And we'll see that. Alternatively, you can use routes, and we have a whole video about routes versus finite state machines elsewhere in the YouTube channel. Pipelines and other workflows should obey ACID principles. In other words, at any given moment in the workflow, the unit of work should be atomic. We should have consistency in the data. One workflow item should generally not affect another workflow item, and the system should be lossless. And we'll talk more about that as we go along. And really good workflow systems try to maximize or allow for parallelism, and that allows the whole system to have throughput. This is especially important for workflows that can't all be done in one temporal line, that have periods where they're waiting for something and are hence dehydrated and rehydrated. We want to be able to, in our workflow, select anything that's ready for processing and have it process in whatever the appropriate step is. And that allows us to have very little downtime if we have messages or workflow data that's in a variety of processing states. In other words, it's some fraction of the way along through its total workflow. I'll throw out a cautionary warning, and that is anytime that you have a requirement that says that, for example, incoming messages or whatever need to be processed in order and in strict order, you should be very, very skeptical of those situations. And in fact, in most real-world workflow situations, such as order processing systems or auction systems, etc., we actually prioritize eventual consistency and fairness as opposed to strict order. If you have scenarios that call for a message processing in strict order, it's very hard to get throughput or stability, because a message that, for whatever reason, is waiting for its next step for a long time will cause all the other ones to pile up behind it. And what we want to do is be liberated from that. And there are a number of really great algorithms for turning things that have apparent temporal dependency and actually making them in order by using a fairness algorithm. So the most basic workflow pattern is the pipeline pattern. And this is often found in, say, web processing. So if you're using Express or ASP.NET, or you're using Spring Boot, what you're building is a pipeline that has a single entry point, the request, and falls through a number of steps, and each step really only has 3 possible outcomes. Either the step is the terminal step and the pipeline exits, sometimes in favor of another pipeline, or the step errors and goes to some error state, which is indeed its own processing pipeline, or the step either ignores the data because it doesn't apply to it and passes through to the next step, or it does apply to it and it will do some sort of enrichment or transformation before passing it on to the next step, right? So one entrance to each workflow step and a potentially 3 exits, of which we have error, return, or next as the choices. In a generic graph pattern, we have a number of workflow steps that potentially have branching in them. If it's this, then go do this other step first, or whatever. And typically those are more successful when they are Q moderated or moderated by some sort of dehydration, rehydration, for a couple of reasons. One is that individual workflow steps might have dramatically different processing times, and Q mediation allows us to independently scale parts of our pipeline. And the other reason is that the messages involved may be awaiting some other processing. And so consequently, it's worth having a Q mediation in a lot of circumstances. And as I commented on the slide, the advantage and disadvantage of this is flexibility. It's very easy to inadvertently have a set of states, particularly if you're using routing instead of a finite state machine, that result in your workflow acting very oddly when you have data that's on the edge cases. Hub and spoke patterns are extremely useful when you are doing message processing or data enrichment or ETL type pipelines. And they typically have a shared topic queue, or in the case of something like a BizTalk or whatever, they have a message box, in other words, a generic dehydration store. And the key to these systems is that the each workflow step does essentially a query on its store and says, are there any messages that match some expression, which is a Boolean expression, which returns true. And if it returns true, the workflow step attempts to process that message. So a couple of things here. One is you have to make sure that the actions on the messages are mutually exclusive. And again, you can assign a finite state machine or a route number or something to make that so. But the advantage is that it's very easy to snap in additional processing steps as long as you're careful. And so these are often used for data comes in, data comes out kind of workflows. So you can think of insurance claim processing or whatever. And because they're storage mediated between each workflow step explicitly, they're effectively Saga. In other words, if workflow step 3 includes a human approval, then the message can stay dehydrated until that happens. So Saga systems are the norm in big, complicated data processing systems. And the point of those systems is to avoid transactional behavior in favor of compensatory behavior. In other words, instead of saying begin transaction, update all these tables, if they fail, roll everything back, we say, okay, well, we're going to get as far as we can get. And if we have to back out data, then we'll go to another workflow path, and that's the compensatory path, and it attempts to back out or repair the changes. Saga systems also focus on managing by exception. In other words, they typically try to be architected so that the happy flows get very little attention, and we manage by exception in that the unhappy flows get put off to a dead letter area or whatever that may have an additional set of workflows, and those workflows may include human intervention. And again, Saga systems are typically very flexible. And because you can implement them on top of any of the workflow patterns we've called out, they tend to be very easy to metricize, right? We simply record that message ID blah, blah, blah has entered and exited this step successfully or unsuccessfully or whatever. And so you can also see and then tune the throughput of a bolus of messages through your system. So there's a couple of different compensation mechanisms. So reversing entries is what's used in bookkeeping. If I am a bookkeeper and I accidentally do a transaction against the wrong account, then double entry bookkeeping says that I don't delete that transaction, but instead I enter a transaction that's the opposite of that transaction. And that's a reversing entry. The other thing is that you can force the workflow to start at a new place in the workflow by changing the finite state or routing state. You can integrate humans to make corrections. You can decide that the message that or data that you're trying to process is hopeless and write it off, put it away somewhere and come back to it later. Or you can attempt to enrich or correct the data that you are dealing with, or some combination of the above. These are all compensation strategies. So, big Saga systems tend to be graphs of graphs. And by that I mean for a particular sub-part of the processing, for example, converting a cart to an order, there might be a subsystem. And then there might be a subsystem that says, well, do I need to split the order into suborders? And then for each suborder, there might be a fulfillment pipeline. And there might be, after the thing is fulfilled and we've sent it to shipping, then maybe that triggers a payment event. And all of those are their own processing graphs. And this is what we mean by Saga systems being graphs of graphs. And again, we should try to make sure that we have a degree of mutual exclusivity so that we don't end up doing something horrible in our processing. And we'll get to that in a minute. And so that's the general philosophy behind making Saga systems, is we take a big, huge workflow problem and we break it into smaller and smaller problems until we have something that makes sense from a granularity, typically driven by some matching set of business processes, and then we make a decision. So you can see that they, in the aggregate, become sort of a graph. And you can see that there are different steps that happen to a message as it might flow through a system. And it is possible to do parallel processing. There are two examples in this graph. One is that we're making a copy of the message state, for example, for auditing. And the other is that we have parallel processing based on the mutual exclusive notion that we either go to the top pipeline or the bottom pipeline, but we're never unsure about which. And then we go and we rejoin a workflow by coalescing the output. This is not to say that the same message goes through both sides, although that is possible using a rendezvous pattern, but it's generally not the best idea in the world. Typically, we want to have differential branches that then coalesce based on the fact that there's something about the order or the message that's special. So, for example, if that set of alternatives was a set of alternatives about shipping methods, I might have different workflows for shipping UPS than FedEx than the US Postal Service, But at the end, I get to a ship complete state, and then I would enter the billing pipeline. And you can have decisions that cause the processing to take different directions. But again, the same message should probably not flow through multiple paths at the same time unless your underlying system has a really good way of doing rendezvous, of recoalescing the messages that you split up and rejoining them in a coherent way. So lots of decision points that you need to think about when you're trying to decide what is the appropriate workflow pattern. And one of the things that we see is kind of an anti-pattern is saying, well, we have the XYZ tool and it does like this. And for this particular use case, I can make it work, but it's not going to be entirely happy. And there are going to be a fairly high number of incidents where a message won't successfully process all the way through my system, and so I'm going to have to intervene somehow. That's kind of an anti-pattern, right? Not every business problem fits into some commercial or open source framework. You need to be flexible and have multiple tools in your toolbox and really consider which things really matter, and use that as a decision driver to choose not only the pattern you're going to use, but the tooling you're going to put that pattern on or implement on. So I guess the takeaway from this is focus on matching the problem to a pattern and then match that pattern to a platform that will support that pattern. I'd be remiss if I didn't point out that there are simply dreadful things that happen in workflow systems. And there are 6 of them, and there's some overlap between the 6, but we've called these out as being things that you really have to be careful of. And it also underlines the importance of having really good monitoring and understanding how a particular message or block of data has passed through our data processing pipeline, and know if something inopportune has happened. So the most obvious one is bit shredding, right? We go through and the message just disappears or the data just disappears. And that's not unrelated to the next one, which is where the system, because it is transforming or enriching the messages, mangles them. And the result is the mangled message is unprocessable. And if we're lucky, it goes into the dead letter box and goes to our attention. But if we're unlucky, it tries to process it and does the wrong thing. And since we're focusing on management by exception, it is a bit challenging because we may never see that we have a malformed message. Cloning messages obviously is dreadful. And it happens when we have workflows that are trying to do a scatter and a rendezvous pattern, but does them incorrectly. And the end result is we end up with duplicate messages. And we can help manage that by having idempotency and having watching systems that very carefully track that and whenever possible, avoid message splitting entirely. Flying Dutchman messages. So we dehydrate as part of our processing because we're waiting for something. And that thing never happens and our message stays dehydrated. And it just sits there. And of course, the way to detect that is to look at the last action state on a message. And if it's longer than a certain amount of time, we go, wow, this appears to be stuck. We need to do something. Messaging is getting routed to the wrong place are a problem. And it happens when our we get to a branch or a split in our processing pipeline, and the criteria are not mutually exclusive. And parenthetically, this tends to be exacerbated by mailbox systems, by hub and spoke systems, because not only can they clone messages inadvertently, but they can have messages go to the wrong place, and that may result in folding, stapling, and mutilating, or messages going dead altogether. And which brings us to ricochet rabbit. Again, if you don't have a strongly linear processing pipeline, and I'm not saying that nonlinear pipelines are bad, I'm just saying if you have them, you have to be able to detect infinite loops where a message goes to some state, is picked up as a result of an expression match, and reprocessed and reprocessed and reprocessed. And so you have to be able to have some metadata around each of the blocks of data you're trying to put through your data processing system, and detect that you have re-entered a particular pipeline set of steps more than an appropriate number. There are times when you want to enrich a message and have it reprocess. But if we enrich the message, the hash of the message by necessity has changed. And so that's a legitimate use case. But we still want to keep track of the number of times that a message has passed through a particular pipeline step. It's rare to see more than one reprocessing loop in a well-behaved workflow system.